So because I've written a fair bit about wood moisture content and wood movement, Wagner sent me a free moisture meter. It's one of those contactless moisture meters, so you don't have to put holes in the wood to measure the moisture. So I've been using it to measure the moisture content of various things around my shop just out of curiosity and because it's so easy. So some of this wood I've been keeping over the ductwork has been getting really dry. So that's one of the lowest readings I've gotten in the house. So why is wood moisture content so important? Because it causes the wood to shrink and expand, and that can really mess up your joinery sometimes. Let me show you. So I made this stool many years ago, and it was in the summer, and I turned that top on the lathe so it was perfectly round, or at least it was when I made it. So to check that, I set these trammel points to be equal to the width or the length of this piece of wood, and now if I put that across 90 degrees, you can see I have a bit of space here. So that's the amount of shrinkage that I've had in this top since I made it. It's now winter, so the wood has shrunk a little bit since summer temperatures. So here's another example. This coffee table was made by my dad a long time ago, and if I measure it lengthwise on the wood, I get 102.5 centimeters. And now if I measure this across, I get just 100.8, so this table is now 17 millimeters less wide than it's long. And that kind of thing can cause major problems. If this table had been attached with mortise and tenon joints to the post, for example, that would have caused a big problem. But you can see down here there's these blocks which allow the top to move with respect to the rest of the table, so that when the table shrinks a little bit, or the top shrinks a little bit with respect to the stand, it's not a disaster. So the catch with wood shrinkage and moisture changes is that it's all a very slow process, and it's hard to visualize because it takes the course of weeks for much to happen. So I'm going to set up a little experiment. So I've got a very thin piece of wood, and I'm going to brush some water on there. And this being very thin, it's going to take much less time for that to change moisture. And I'm going to time how long that takes, and I'm going to take a time lapse of that with another camera. So let's do the experiment. So I'm going to wet just one side of this piece of wood. I'm going to put that side on the bottom just so the water doesn't evaporate right away. And put it on this clock, and now we wait for things to happen. Well, isn't this an exciting video? Let's switch to time lapse. So after more than 2 hours, there's no wetness left on here, and this water has migrated into the wood a little bit, which is why we have this bow to it, but it's more moist on this side than it is on this side, so it certainly hasn't equalized across the wood. Otherwise, we would just have a straight expansion. And I measured this piece of wood to be 20.35 centimeters across, and if I now force it flat and measure it again, it's now 20.4 centimeters across. So in this short time we've already gained 1.5 millimeters, and we can't really, it's not like this wood is wet. So if it had equal amounts of extra moisture, we would have probably gained about 3 millimeters on the width. So that's a way of accelerating seeing some of this, but even so I had to wait over 2 hours. The wood mostly shrinks and expands in this direction, perpendicular to the grain, and hardly any in the length of the grain, and there's two ways of dealing with that. One is to just allow the wood to move, the other is to overpower it. So for example, with plywood we have grain in alternate directions, and it's always the lengthwise grain that overpowers it cross grain, because lengthwise the wood is much stiffer. So if there's enough of extra wood holding it from changing width, you can just overpower it, and I'll just put this wood here in a vise and I'll show you how it has flexibility in that direction. So let's measure that, and I have 37 millimeters here, and if I now apply a bit of pressure, each turn on here is 2 millimeters, so I've just squished this wood by 2 millimeters. So the flex in the wood can make up for anything that it wants to shrink or expand if we hold it firmly enough. So with the bandsaw frame, for example, I have the wood grain coming out from these pieces and alternate pieces that comes from the bottom. So these pieces don't shrink and expand at the same rate, but because they're all sandwiched together, basically the cross-grain shrinkage and expansion can't happen because the long grain of the other pieces holds it in place. And this glue joint doesn't pop apart and everything is still level here. Where people run into problems is if you want to put, for instance, some edging on this butcher block here by just gluing another piece along the side of it. So this block will want to shrink and expand a little bit, and there's no way this glue joint or this piece of wood will prevent that from happening, which means this block is going to shrink and expand, this part in this direction much less, and the glue joint is what's going to have to give. Which is why if you put a rail on the end of a board like that for a table or something like that, you always use a joint where you can have a little bit of sideways slippage to accommodate for the shrinkage and expansion. Now some people say I don't need to worry about this moisture changes because I'll just put a good layer of oil or varnish on there and then the moisture can't get in and out. But that's not really true because plastics to some extent are all permeable by water vapor, and so things like a potato chip bag are always shiny on the inside because they put a thin layer of aluminum in there because the metal is actually much better at keeping the moisture from going in and out, so that way your potato chips won't go soggy. Same thing for granola bars and other little snack bags. So moisture meters work by measuring electrical properties of the wood, but the Wagner meter doesn't actually have any electrical contacts on the back. It uses high frequency and with that measures the electrical properties of the wood. So if you just place it on the wood, wait for it to turn on, it capacitively couples and uses high frequency. This meter, for example, used to have prongs and you had to whack it into the wood. Only problem is the plastic wasn't strong enough and it broke soon afterwards, so I put a separate set of contacts on there which I could then whack into the wood with a hammer to get a reading.